Hello everyone, welcome back. I am Vijay and today we shall explore how to control a stepper motor using an Arduino. Stepper motor is a brushless DC motor and is known for its precise control in applications like 3D printers, CNC machines, robotics, and many precision control machines. We shall learn construction and working of stepper motors, the coil arrangements, unipolar and bipolar, and the excitation of coil for full step, half step, and micro stepping. I shall also demonstrate the control of 28 BYJ48, the unipolar stepper motor using ULN2003 motor driver, and NAMA 17, a bipolar stepper motor using L298N and A4988 motor driver for constant steps, acceleration, and deceleration. The control will be carried out with and without libraries. So there are a lot of things in today's session. Here is what we will be using for this tutorial: an Arduino board, a breadboard, stepper motor. We shall use NAMA 17 and 28BYJ48, LN298N, A4988 and ULN2003 motor drivers, 5 volt and 12 volt external power supply, ratiometer of around 100 kilo ohm and few jumper cables. So let us get started. To begin with, let us see what are the different types of stepper motors. There are three types of stepper motors: permanent magnet, variable reluctance, and hybrid stepper motor. The rotor of a permanent magnet stepper is constructed with permanent magnets having alternate north and south poles and interacts with electromagnets of the stator to create rotation and torque. Whereas the rotor of variable reluctance stepper motor is made up of plain iron with gear-like teeth around the circumference which interacts with the electromagnet of stator to create a path of least reluctance. Just to remind, reluctance refers to the resistance offered to the passage of magnetic flux. It is analogous to electrical resistance of electric circuit. The last type is the hybrid stepper motor. The rotor of hybrid stepper motor uses the best features of both permanent magnet stepper and variable reluctance stepper. The rotor in a hybrid stepper motor has a permanent magnet core, while the circumference is built from plain iron and has teeth. Now let us understand how stepper motor works. When a coil of a stator is energized, it develops electromagnetic poles. A magnetic rotor aligns along the magnetic field of the stator. The other stator is then energized in the sequence so that the rotor moves and aligns itself to the new magnetic field. This way, energizing the stator in a fixed sequence rotates the stepper motor by fixed angle. The clockwise rotation of rotor is achieved by counterclockwise energizing sequence. The sequence is reversed for counterclockwise rotation. The equilibrium position of the stepper or the step in one revolution is equal to the product of rotor poles and the stator pole pairs. So, 360 divided by the step per revolution gives step angle. For this example, the rotor teeth are 6, stator pole phases are 2, pole pairs are 2. So, there would be 12 equilibrium positions. This will give us step angle of 30 degrees. Permanent magnet stepper guarantees a good torque and also a detent torque. This means the motor will resist to a change of position regardless of whether a coil is energized or not. A permanent magnet head has a lower speed and lower resolution. In case of variable reluctance, the rotor of the variable reluctance motor is made up of plain iron with gear-like teeth around the circumference. The teeth of rotor are aligned with one of the energized stator pole and other teeth get misaligned. Now, when the next stator is energized, the rotor moves to align its teeth with next stator pole. The teeth lead variable reluctance steppers to reach a higher speed and resolution but provides low torque and has almost no detent torque. The resolution of a stepper can be increased by increasing number of teeth on the rotor or by increasing the number of pole pairs. Now, coming to the hybrid stepper motor, this configuration allows the motor to have a advantage of both permanent magnet and variable reluctance versions, specifically high resolution, speed, and torque. The magnetic rotor has two cups with alternate teeth and is magnetized axially, one for north pole and second for south poles. Recall the expression of equilibrium position. If we take example and assume that 50 teeth on rotor and 4 pole pairs, then in that case there would be 200 steps in one revolution. So step size comes out to be 1.8 degree. We will explore this in more detail in later part of this session. We cannot just connect power to the coil to operate them. Instead, we have to energize the two phases in both directions by sending pulses in a particular order. There are several ways of driving the stepper motor. The first, single coil excitation or wave mode. The coil excitation that we just discussed, where one coil is energized at a time, is called wave mode. We can see this from the figure that initially coil A is energized, followed by coil B, and coil A is then de-energized. Then coil B is de-energized and coil A is energized in opposite polarity. This is represented by high signal through A dash and so on. In full step mode, we see there are two coils energized at a time, starting from AB dash followed by AB, then BA dash and then A dash B dash. The same sequence is repeated. This mode increases the torque capacity, but the resolution remains same. For increasing the resolution of stepper, we use the half-step drive mode. This mode is actually a combination of previous two modes. Here, we have one active coil followed by two active coils, and then again one active coil followed by two active coils, and so on. We can see the waveform and observe that coil A is energized initially, followed by A and B, then B followed by B and A dash, then A dash and A dash B dash followed by B dash. And so with this mode, we get double the resolution with the same construction. Now the rotor will make full cycle in 24 steps. The resolution is changed from 30 degree to 15 degree. However, the most common method of controlling stepper motors nowadays is microstepping. Microstepping is a method of controlling stepper motors typically used to achieve higher resolution or smoother motion at lower speed. In this mode, we provide variable controlled current to the coil in the form of sine wave. It is achieved by using pulse width modulated voltage to control current to the motor windings. Microstepping divides each full step into smaller steps to help smooth out the motor's rotation, especially at low speed. For example, a 1.8 degree step can be reduced to a step angle of 0.007 degrees or 51,200 microsteps per revolution. To accomplish all these excitations and the directions, we need specific drivers for controlling the stepper motor. There are many types stepper motor drivers. However, they work on the basic principle of 2H bridges to allow energizing the coil in both directions. We can use LN L298N motor driver to control a bipolar stepper motor, but it cannot provide the functionality of current setting and microstepping. So we use A4988, which has the functionality like micro stepping and current limiting, and that we will be demonstrating in the later part of this session. The stepper motor can be unipolar or bipolar depending on how the coils are connected. In bipolar stepper, there is single winding per phase. The direction of current need to be changed by driving circuit, so that driving circuit of the bipolar stepper become complex. In unipolar stepper motor, there are two windings per phase, so the unipolar motor so have 5, 6 or 8 leads. In the designs where the common of two poles are separate but center tap, motor have 6 leads. If the center tap of the two poles are internally short, then motor has 5 leads. 8 lead unipolar facilitate both series and parallel connections, whereas 5 lead and 6 lead motor have series connection of the stator coil. The unipolar motor simplifies the operation because in operating them there is no need to reverse the current in driving circuit. Now it is the time for demonstration. For demonstration purpose, we shall take NEMA 17 hybrid stepper motor. The number 17 in NEMA 17 gives the size of square face plate in inches when divided by 10. So NEMA 17 will have face plate of 1.7 inches. NEMA 17 has a resolution of 1.8 degree, which is equal to 200 steps in one revolution for a full step excitation. To ensure proper motor performance, it is important to use a power supply that matches voltage and current rating of the motor. For example, if we want to run our motor at 1 ampere, then we can find the voltage using Ohm's law and coil resistance. It is the driver which ensures the supply of required power to motor by manipulating voltage and current. Since the motor draws too much power, it is suggested to power it directly from an external 5 volt or 12 volt power supply rather than drawing it from a microcontroller. Running motor 5 volt pin is not good and could burn out the 5 volt regulator if running from batteries. L298 is the motor driver that we generally use to control two-brushed DC motor. But we can control one bipolar stepper motor using the same. To connect to any driver, we have to find the coils of bipolar stepper first. We can use a multimeter and check for continuity between two wires. If you connect two wires that make a phase, you will have a short circuit and the multimeter will start beeping. Once we find a phase, we can connect it to any position of the two positions on the driver. The order doesn't matter. The connections are easy. Connect coil 1 to one motor output. The sequence doesn't matter as we have already discussed. The coil 2 is connected to other motor output. We can use 5 volt or 12 volt external power supply and keep the strap onto the power to power the logic circuit. Now connect the logic pin IN1, IN2, IN3, IN4 of the driver to the Arduino pin 8 through 11. Keep the enable pin I through logic pins or keep the straps on both enable pins. That's it. Coming to coding. Open the Arduino IDE and open the stepper example code. You can open this code from this example and stepper 1 revolution. So this code needs some modification and I will put some comment and then we'll discuss. So this is the modified code. It is rather modified only in terms of the comments that I have put. We can start with the stepper motor library that we can include. And then, as we know that the stepper revolutions are 200 in NEMA 17, and we have connected the IN1, IN2, IN3, IN4 to 8, 9, 10, 11. So that is what basically we have mentioned in creating the object stepper. And we can set the speed of 60 RPM, and then we can experiment. Let us first upload this code and see the result of this. We can see that our motor is running and some sound is coming. We can also open the serial monitor and that will print clockwise and anti-clockwise rotation. So we can now change this to 100 RPM and see how the motor is running. Upload the code and see how the motor is running slightly faster than this. Now change this to 200 and upload the code. The speed will increase to 200 RPM that we can see from the output. Next, make it 300. We keep on increasing this to check what is the maximum RPM that this particular motor can have. So 350, if we change and upload this code, you will find that the motor started skipping the steps. So we have demonstrated how we can connect stepper motor using L298 motor driver. Next, let us use A4988 motor driver. We can see the datasheet of A4988 and we can find the maximum current rating. It's 2 ampere. It is recommended to keep the current maximum up to maximum current rating of the motor. Efficient cooling must be provided for higher current. Use of A4988 makes it possible to set the maximum output current to the motor to make the motor safe and avoid the overheating of the motor which may damage it later. This is achieved by the potentiometer given on the driver module. However, we should set the current limit lower than motor maximum current to be on the safer side, subjected to the torque requirement. Here, it is also recommended to use decoupling capacitor across these two pins in order to protect the board from voltage spike. We can safely use 47 microfarad capacitor. Next, we have logic power supply pins VDD and ground, which can be from 3 volt to 5 volt. On the other side, we have the step and direction pin, which can be connected to any of the Arduino board. With the direction pin, we select the rotation direction of the motor, and with the step pin, we control the step of the motor. With each pulse we send to step pin, the motor will advance one step in the selected direction. Above this is the sleep pin, which is active low and used for putting the driver to sleep mode. The sleep pin is default high. Next is the reset pin for resetting it, which is also active low and used for resetting the driver. We can set it high by connecting it to sleep pin, which is internally high. The enable pin is also active low, so unless we pull it high, the driver will be enabled. The next three pins, MS1, MS2 and MS3, are for selecting the step resolution of the motor. We can use this logic table to achieve the micro steps given. For example, if we select quarter step resolution by setting MS1 to low, MS2 to high and MS3 to low, the NEMA 17 will have 800 steps per revolution. The driver will use 4 different current levels on the coil to achieve this. The A4988 driver has a maximum resolution of 16 microsteps, which would make a 200 steps NEMA 17 motor to 3200 steps per revolution motor, or that is approximately 0.1125 degrees per step. By default, these are set low using pull-down resistors. So if we want only full step mode, these may not be connected. We can set current limit using the potentiometer. And for setting the current, we have to calculate reference voltage. We can find the formula for reference voltage for A4988 is the current limit multiplied by 8 multiplied by current sense resistor. The resistance value is generally mentioned on the current sensing resistor, and for the desired current limit on the basis of maximum motor current, we can calculate the reference voltage. So the resistor we can see is 100 milliohm, and let us assume 1 ampere current against the maximum 1.5 ampere current for NEMA 17. So the reference voltage will be around 0.8 volt. To set this, we can use the multimeter and measure the voltage. Connect multimeter common to ground and positive to screwdriver as shown in the figure circuit diagram. We can power the logic voltage through Arduino. Now adjust the potentiometer screw till the multimeter reads 0.8 volt approximately, which is the desired reference voltage. Now we are ready to connect the driver with NEMA 17 motor. Connect the motor and Arduino to the driver as indicated in the circuit. So coil 1 to 1A and 1B, coil 2 to 2A and 2B, use 9 volt to 12 volt, rather 5 volt to 12 volt power supply, and connect to V motor and ground through a decoupling capacitor of 47 microfarad. Short reset and sleep to make it high, as sleep is internally high by default. Finally, DIR and step to digital twin 3 and 2.